Hello, my name is Yannis Kamitsos, and the other members of my team are Sank Teha and Jessica Bawa. My talk is titled Optimal Sleeping, which refers to optimizing energy consumption in computing and communication infrastructure. Before starting this talk, I'd like to thank some people who helped a lot in setting this project up. First of all, Professor Lachlan Andrew, who is a professor in Australia, Swinburne. Dr. Hong Song Kim, who used to be a postdoc in our group and now is working at Bell Labs, and also Paschalis Tsiaflakis, who is a postdoc in Belgium. What is the motivation behind our work? There are several reasons, economic, environmental, and also the concern of overheating, which imply that reducing the energy consumption of computing and communication infrastructure is very important. The information and communication technology sector represents 2 to 2.5% of worldwide energy consumption, and this share is predicted to increase over time. So greening this sector will be beneficial to other areas of the economy as well. What is the problem we're trying to tackle? Basically, we seek to find the Pareto optimal trade-offs between energy consumption and performance when we activate sleeping mode operation on devices such as servers or DSL modems. However, saving energy is not trivial because it takes time and also a significant amount of energy to turn on or turn off infrastructure, like devices like, as I said, servers or DSL modems. Also, there is a price that needs to be paid, and this price is a delay and stability. Here you can see the problem taxonomy. Specifically, in terms of reducing energy consumption, we focus on two different areas, computation and communications. In terms of computation, we focus on a homogeneous server, and every homogeneous server we assume that consists of different homogeneous cores. And also we focus on heterogeneous servers in terms of large-scale data centers. In terms of communications, we focus on wireline broadband access, specifically DSL broadband access, which is the dominant wireline internet access nowadays. First of all, I'd like to focus on sleeping in data centers. Over the last years, cloud computing has become significantly more important, and data centers nowadays are most of the time underutilized. The average data center utilization is around 20 to 30%. This means that significant amount of energy is wasted on idle mode. That's why we propose sleeping in order to overcome this drawback and actually save the energy that's wasted by device idling. However, designing an optimal sleeping policy is non-trivial. As I mentioned earlier, entering and leaving sleeping mode requires both energy and time. Also, choosing the best point of the energy performance trade-off depends on the relative importance between how fast jobs are being processed and how important energy savings are. So we modeled the problem, we solved it, and here you can see the optimal sleeping policy when we study a homogeneous server which depends which consists of multiple independent homogeneous cores. The optimal sleeping policy is monotone hysteretic threshold based. This means that there are on thresholds and off thresholds in terms of waking up or putting cores to sleep. Here in the graph you can see the x-axis represents the number of jobs in the buffer and the y-axis represents the number of cores that are awake at any given instance. As the number of jobs in the queue increases and we successively hit the on thresholds, this means that we successively wake up the cores. And once all the cores are awake, as the queue is being drained and we successively meet the off thresholds, then we successfully put cores to sleep. I need to add that we implemented this sleeping algorithm and the sleeping policy on the EdgeLab experimental testbed, and we compared the theoretical predictions with the experimental measurements, as I will show later. These two graphs demonstrate the advantages of resource pooling in homogeneous servers. You can see from the first graph, which corresponds to the energy performance trade-off, but compared to a single core case, as we increase the number of cores in the system, the performance becomes better. However, there is a critical point that the performance won't become better as we increase the number of cores indefinitely. The second graph demonstrates the robustness of the system. Specifically, every time we want to optimize the system, we optimize it for a given traffic load. However, the actual traffic load in the system can be different. But as the number of cores are under our control increases, then the system becomes more robust to this kind of traffic load misestimation. This graph here demonstrates the energy savings that can be achieved by applying our optimal sleeping policy. Specifically, the x-axis demonstrates the traffic load and the y-axis demonstrates the energy savings. For lower traffic load, we can see that the energy savings are more significant, and specifically for let's say 20% of traffic load, the energy savings can reach the theoretical maximum of 80%. Of course, as traffic load increases, then the energy savings naturally fall, because having significantly higher traffic load, this doesn't allow the servers to sleep for a long time. Here you can see the experimental testbed that we used in order to implement our algorithm. First of all, we have a set of servers that connect to different power meters, which log power measurements every second. Also, we implement a controller which basically runs the optimal sleeping policy calculation algorithm, and also generates jobs according to a Postman process. In addition, the controller monitors a buffer and sees how many jobs are waiting to be processed, and every time a specific on threshold or off threshold is met in terms of the number of jobs in the queue, the controller turns on or turns off specific servers according to the optimal sleeping policy. Also, the controller distributes jobs to available servers, and for jobs we used video encoding applications. This slide here demonstrates the comparison between theory and practice. The graph to the left demonstrates the energy consumption average delay trade-off derived by theoretical simulations, and the graph to the right demonstrates the energy consumption average delay trade-off that we got by experimental measurements after implementing the system I described earlier. We can see that the theory makes a pretty good prediction of the experimental energy performance trade-off, as can be seen by the shape of the graph. However, there are differences. For example, the order of magnitude of the energy and delay values. During the implementation of this system, we had several issues that we had to face. For example, sometimes we had multiple jobs being assigned to the same server, and also sleeping or wake up commands would be issued in the middle of other commands. These were some synchronization issues that we had to fix. And also, several times, the wake up or sleeping time wasn't fixed, wasn't as predicted, but was varying. And also, the switching cost demonstrated some spikes, which made the system a little bit unstable. Next, I'll focus on heterogeneous servers, by noting that large-scale data centers consist of hundreds of thousands of heterogeneous servers. Until now, we studied a homogeneous server where we made decisions on an arrival-departure timescale. However, when we go to a large-scale data center, we have a second level of decisioning. It's a slower timescale where we make decisions every time a speed requirement in the data center changes, and this decisioning corresponds to putting subsets of servers to sleep or wake them up. So we suppose we have several different types of processors, where we have multiple processors of the same type. Here you can see the problem formulation. Basically, we aim at minimizing the total power consumption in the data center, subject to the constraint that the total speed stays above some fixed speed requirement in the data center. This problem is very similar to a knapsack problem, and we solve it via a greedy algorithm which we show that performs within 60% of the optimal solution. Here you can see the system performance. The first graph demonstrates the power consumption speed requirement trade-off for the heterogeneous problem, and we can see that the convex power model that is often assumed for speed scaling schemes is also applicable to cases where we turn on or off cores or servers. The second graph shows the heterogeneous setup gain compared to an average homogeneous case which is a hypothetical scenario where each server consumes an average amount of power and runs on an average speed. We can see that for lower speed requirements, which is the area that saves power, the heterogeneous setup gain is much more significant compared to an average homogeneous case. Another application that we focused on and we applied our slipping techniques was the DSL broadband access, which is the dominant wireline broadband access nowadays. The good news is that DSL already implements a slipping mode, however it has not been yet exploited completely due to stability concerns. DSL is interference limited, which means that within the same cable bundle where we can find the DSL lines, when the DSL lines turns on, then this increases the crosstalk in the bundle and can make other lines unstable. So, while applying our slipping theory in DSL, we also provided some techniques that can guarantee stability in the cable bundle. Here is the system that we studied. We can see that we have several DSL modems. Each modem has a buffer which accumulates jobs. And what we're trying to do is optimize the transmit powers by choosing from on to off, between on and off, for each modem, so as to find the trade-off that optimally balances energy and delay for given input arrival statistics. Here you can see the techniques that we proposed in order to guarantee stability in DSL infrastructure when slipping is applied. In the time axis, what we propose is to introduce some intermediate states between on and off, so as to make the wake up of lines gradual and give the other lines in the cable bundle the opportunity to adjust, the time to adjust their noise margins so as not to become unstable. In the space dimension, we limit the number of lines that can wake up or go to sleep at the same time. So this would result in the crosstalk reduction in the bundle. And in the frequency dimension, we don't wake up or put to sleep all the frequency tones at the same time, but we split the frequency band into two subbands, and we wake up or put to sleep different subbands at a given instance. Here you can see the three-way trade-off between energy, delay, and stability that is introduced in the DSL infrastructure when we apply our slipping algorithm. In the first graph, you can see the energy consumption and average delay trade-off for different number of intermediate states between on and off. And you can see that as we increase the number of intermediate states, in other words, as we make the wake-up of the lines more gradual, then the performance deteriorates, which is normal because it takes more time for the modems to fully wake up and transmit data. But at the same time, as we introduce more intermediate states, the system becomes more stable, as we can see from the second graph. Specifically, let's say for three intermediate states between on and off, the maximum noise impact improves by 70% compared to a case where a modem wakes up without any intermediate states between off and on. And on top of that, as we limit the number of lines that can wake up at a given time, then for given number of intermediate states, the maximum noise impact improves. In summary, summarizing my talk, we saw that slipping results in significant energy savings, but applying a slipping policy is not trivial and also requires paying in delay and stability. Also, I showed the optimal slipping policy which we implemented on an experimental testbed. We compared the theoretical predictions with the experimental data, and we found that theory makes a pretty good prediction. And also, I demonstrated how resource pooling improves both performance and robustness against traffic load misestimation, and at the same time, how heterogeneity further sweetens energy delay trade-off. And finally, I showed that in DSL broadband access, slipping can be feasible and can also be stable, and at the same time results in significant energy savings. Thank you.